before I get started, I wanted to kind of just ask some questions of the room. So how many people are using ZFS? Awesome. How many people are using it on Solaris? How many people are using it on Illumos? FreeBSD? Linux? Sweet. OS X, Mac OS. Ooh, one brave soul. Awesome. So a little bit about myself. I started out my career on ZFS working at Sun Microsystems. I started in 2005, just as we were rolling ZFS kind of out into the open. One of my first big tasks was to actually take it into a shipping release. So I was responsible for actually bringing it into Solaris 10 and making the first release available for revenue. After working at Sun and Oracle, I decided to actually try other ventures and move to a company called Delphix. Delphix actually heavily utilizes ZFS. We are a big contributor to open source, and we've kind of committed to being a contributor to open source. But today's talk is really about OpenZFS and ZFS for everyone. And that should really have like a little star there, because sorry, Microsoft, nobody has come up with a ZFS port for Windows yet. But at least it's there on many platforms. So a little bit of history about ZFS. So it started in 2001. Two developers, one of my colleagues, Matt Ahrens, who works at Delphix, and another good friend, Jeff Bonwick, were the two engineers that actually started ZFS in 2001. And finally released out into the open in 2005. 2006 was the first time we actually shipped ZFS to customers. And in 2008, we had a FreeBSD port that was actually pretty stable at the time. FreeBSD, by the way, is pretty much in lockstep with what's happening in the Illumos community. And I'll talk a little bit about how these various communities are kind of coming together. And we're seeing different pieces of development happening everywhere. So it's pretty cool. And then, as many of you know, in 2010, after Oracle had purchased Sun Microsystems, the OpenSolaris project was taken away, and code that was actually being released from inside Oracle to the open source community just kind of shut off. And right around the same time, the Illumos project actually started to flourish, and it really became kind of the first truly open source version of a Solaris derivative out for the community. Just this year, we had a stable version of ZFS on Linux, and just a few months ago, we announced OpenZFS as the first truly open source successor for ZFS. And I say truly open source as a distinction there. When ZFS was being developed and available, when Sun actually was pushing things out to the community, there wasn't a lot of development that was actually happening outside of the gates of Oracle and Sun. Everything was kind of being driven through. We had a few contributors, but the majority of the work was actually being done by engineers at Sun and Oracle. We were just kind of pushing it out. This is actually quite different. We're actually seeing development projects coming from all sorts of different contributors, all sorts of industries. It's pretty terrific. So that leads me into what is OpenZFS. So OpenZFS is kind of, you can think of it as an umbrella project. It's bringing together communities for three main goals. We want to raise awareness of ZFS on various platforms. We want to make sure that we have open communication so that people are aware of like what's being developed where. We don't duplicate effort. We all are trying with one goal in mind, and that is to promote ZFS on regardless of, what platform you run. And three, we want it to be consistent. We want to make sure that if I develop something on Illumos and somebody else develops something on FreeBSD, that at the end of the day, they behave the exact same way, regardless of whether you're running Linux, Mac OS, Illumos, FreeBSD, doesn't matter. OSV. So there may be a fourth community coming. So if you How many people are aware of OpenZFS or heard something about it? Oh, cool. Great. So this is the website for those of you that are not aware of it. It is primarily like I said, it's kind of a meta community. You'll find documentation, pointers to all the different communities that are out there. So if you want to find out like where is the ZFS source base for Linux, you can actually go to openZFS.org. You'll find a link for it. It'll drive you to their website. We're also putting together a lot of pieces around the development process because we're trying to come up with a consistent model that makes it easy for all the different platforms to actually develop something and quickly distribute it out and spin up new releases. We want to get away from the point of actually having very specific code that is designed for a Lumos and then has to have kind of tweaked and turned in order to make it work on Linux. So we're trying to get away from that. Definitely check out the website. There's a lot of resources. We're adding more resources to it pretty much every day. So with that in mind, this is what we're hosting today. So we have the 4 different communities, a huge number of committers that are coming in, and lots of contributions that are happening from all of the different platforms. And what's really interesting about this is it's also driving a huge number of companies to actually take OpenZFS into their platforms and come out with something, whether it's an appliance, a general purpose OS, all sorts of different things. We have companies that are doing it for security, like Wheel Systems. Delphix, the company I work for, works on database platforms. I know we have folks from Joint in the room, general purpose computing platform. So lots of different things. The telling factor here is that whether you're using it on Linux, FreeBSD, or Lumos, OpenZFS is actually becoming a very big driving factor to platforms that are spawning off new companies. And for this list that you see here, there's probably hundreds, if not thousands, of other companies that aren't named that maybe are in their starting phase that don't want to be named, but hopefully eventually this list will continue to grow and flourish. Okay, so kind of the fluff pieces to OpenZFS and what OpenZFS was all about. Well, when we started actually thinking about how do we bring these communities together, and we actually started this back in 2010, just at the time that my colleague Matt Ahrens and I had joined Delphix. We knew that we wanted to try to drive this community and kind of make it easier for it to build and flourish. So one of the very first things that we had to figure out is how do we deal with features that are being developed across different platforms? So I saw many hands that had raised about Solaris. So on the Solaris world, when we were doing on-disk format changes, it was just this linear fashion. You went from on-disk version 28 to 29, couldn't go back, but it was just this incrementing integer that eventually will hopefully never wrap. God, I hope not. But that wasn't going to work in the open source community. I couldn't have a Linux developer building version 30 if I'm building version 30. And we didn't want to have a mechanism where I have to ask some website or some administrator, can you please hand me, I want to check out the next version number. That didn't make any sense. So the idea behind feature flags was an ability to actually put names behind features and make each feature addressable in its own right. So we actually have the ability to have a feature that you can turn on. If it's turned on a FreeBSD pool, it might even be read-only compatible in such a way that if I take that same pool to a different platform, if it's read-only compatible, that means that I can't actually write it, but I could still look at the pool. I can look at its content. There's also ways for features to be enabled but not necessarily active, which means that I turned on the feature but I've just never used it. So in that case, the pool itself is still transportable and can actually be and is portable across the different platforms. So if we look at some of the features that are out there in OpenZFS today, and these are just on-disk format changes. So there's many more features, but these are the ones that have actually changed the way things are being written to the pool itself. We currently have 5. I'll say there's more queued up, so stay tuned. But you can see that the naming scheme has actually dramatically changed. Now things actually have a name, and when you create the pool, you actually get to set them. So this is the administrative way that you would actually go about setting, for example, async destroy. You enable this feature when you want to use it. Once you've enabled it, if it has to go to a platform that doesn't have it, then you'll get an error saying that that platform doesn't support that feature if it doesn't allow you to have read-only import. If it has read-only import, then you can say, you can import this read-only and actually look at the data, but we won't actually let you write it. So in the previous slide, I mentioned LZ4 compression as one of the new features that came in. And what's interesting is, how many people are using compression on their pools today? Anybody using gzip as compression? Few people. So most people, I assume, probably using LZJB, which is a great, very fast, very efficient way to compress your data. What's interesting about LZ4 is it actually turned out to be much faster than what LZJB could actually drive. We saw that its decompression in particular was quite impressive. You can see from this chart that we're actually able to drive almost twice as much work than LZJB, and its compression percentage is higher than LZJB. So this became a very compelling argument for us to bring this into the OpenZFS repo because of its benefits that it brings to it. Naturally, when we actually said, okay, now we have LZ4, what's the next thing that we could do with it? The compressed L2 arc came into the picture. L2 arc users? Okay. Anybody using compressed L2 arc? Has anybody tried it? So what's interesting about the compressed L2 arc, and in this case, this chart, this is actually available on the Illumos website if you want to look at some of this data. The test was actually using a 60 gig L2 arc device. And what this is showing you is that if you didn't, this bottom line, the blue line, if you didn't actually have an arc enabled, this is the number of reads you could drive out of it. So you're getting somewhere around 10,000 K, is that? Yeah, it's all in K, kilobytes. If you have 40 gig worth of data. And obviously, as you increase the amount of data on there, then you're pretty much, you're driving the throughput down. Well, you add the red line, which is just a simple L2 arc. We're actually able to read more data because we're now caching a good portion of it, but it starts to drop out as soon as you get to the maximum size of the L2 arc. So you can see there around the 80 gig mark, when the working set is much larger than the L2 arc, we start to see performance degrade. Well, with LZ4, we're able to do about a 2x compression. So in this case, we're actually able to pretend that that device, that 60 gig device, can almost drive 120 gig worth of read data. So it's quite impressive to actually use it with minimal overhead. And that was one of the big driving factors why LZ4 has a really nice chain. It is not the default compression algorithm today, but it would not surprise me if in a few more months that we don't change the behavior where you say ZFS compress equal on to actually mean ZFS compress equal LZ4. To actually having compressed L2 arc? I would say it's probably too early to tell. We haven't really seen much downside with actually having the compressed L2 arc, and I'm not sure we have as much experience as we need. Definitely with LZ4, we haven't seen a downside at all. Yes? So the question was, have we seen a difference in CPU utilization using LZ4? Our experience has been that it is negligible. So at Delphix, for example, we run all our ZFS file systems have compression enabled, and we're actually getting CPU back as a result of using LZ4. Now, LZJB was actually a very, very efficient compression algorithm, so it's negligible in that case. But if you're a gzip user, I would imagine you would see quite a bit of resource that actually comes back if you switch from gzip to LZ4. Question is negative effects on dedupe. With LZ4, I don't know, quite frankly. I don't have performance data on that. I would imagine that the answer is no. It's hard to have more negative effects on dedupe. Sorry, I worked on dedupe, so I can actually, I can actually rip on it. I think that was one of the things that I signed when I worked on dedupe, was that you can actually make fun of it later. Another thing that has just recently come into OpenZFS is a enhanced right throttle. So first let me describe a little bit about why we have a right throttle and what the old one looked like. How many people are familiar with the right throttle? Ever heard of it? Okay, so yeah. So the reason behind the right throttle is that applications, as they're writing, are typically just writing to memory. And you can imagine that you can come up with an application that can just overwhelm and write to memory as fast as possible. And if your back end, your spindles are actually quite slow, you get into this bottleneck where you've created all this dirty data in memory that you're now trying to flush out to disk. So every single time you flush things out to disk, it's like everything is going to kind of stall behind it. We might even see situations where you're running out of memory simply because you've been driving it so hard and we can't keep up on the back end. So as a result, the right throttle was created. And the idea behind it is that as you start reaching a certain amount of dirty data in memory, you start to throttle your individual clients. So if you have an NFS workload, the NFS writes will actually stall. They'll go into a kind of a wait cycle. We started looking at this problem. One of the things that we observed was that that wait cycle meant that you were, in many cases, having to wait for an entire transaction group to commit. Now, if you're using Solaris or Illumos, most of the commit write cycles try to stay in a 1-second cadence. So every second we're trying to flush out a transaction group. Well, if you're a latency sensitive workload, having to wait for 1 second is kind of a killer for you. So as a result, we wanted to kind of do something about it. And my colleague Matt Ahrens actually coined this phrase, the brick wall of wait, which is exactly what we were seeing at Delphix, was a massive workload coming through and lots and lots of threads that were all blocked, in many cases for 1 to 10 seconds. So this is a histogram that we put together with some of the data that we collected. And what we were able to see was that normally when you're driving a heavy write workload, you would get into instances where the writes are actually serviced quite quickly, in the sub-millisecond range. As we would expect, we're just writing to memory. But the problem is that once you hit that threshold, you would get into situations where you start to peak on the opposite side of this chart, where you're seeing outliers that are approaching 10 seconds. And you can see that peak starts to actually climb quite rapidly. So we're seeing lots of outliers in that region, and that's exactly what we're trying to address. So if we look at the new write throttle, what it does differently is it simply starts to track the amount of dirty data that you're writing to the pool. And we already had tracks, accounting that we did this for transaction groups, but we wanted to do this across everything that's being written to the pool so we can figure out how these things are being updated. The other thing that's interesting is that we didn't actually have a way to tell, in this case, the ARC or the DMU, how much data had already been committed. So if you had a gigabyte of data to write, you had to wait for that entire data to be written for it to know that it could proceed. In this instance, what we're doing now is, if you have a gigabyte to write, and some of those writes are starting to, get serviced, as those writes are getting serviced, we're actually calling back and saying, okay, yes, I just wrote 100 meg. I can take 100 meg more of dirty data again. Oh, I just wrote, 500 meg. I can take 500 meg. So we don't have to wait for the entire gig to write to disk. We're taking them as they're getting flushed out. This meant that we could actually slow things down gradually, rather than having this very steep cliff where we all of a sudden, have no more memory available to us and have to force everybody to wait. So as a result, we can actually delay individual clients gradually, and as the data starts to get consumed or memory starts to get consumed, we increase the delay even further. So when we chart the two pieces and take a look at what this did for us, we actually found that the new write throttle allowed us to have this tighter curve. So again, this orange is the histogram that we got by doing the exact same workload. And we saw that most of the writes are now being serviced in a millisecond. We have very few outliers. The largest outliers we were seeing were 30 milliseconds. So we're more constrained. We've been able to actually constrain the latency by using the new write throttle versus the old way where we actually had everybody wait. In addition to that, we added these per IO type device queues. Prior to this, what we had in the VDEV layer was you had this mechanism where as writes would get queued to the disks, they would get sorted based on time, which seems kind of intuitive, right? One guy came in earlier, so let him go first. We would add this additional kind of factor to it, and that was based on some priority. So if you had reads, we felt reads were more important. Synchronous writes were more important than async writes. So there was kind of a slight factor to that. But you could get into cases where you would end up, like when you were doing a transaction group commit, all these asynchronous writes would come in, and then a read is bottled up behind it, which meant horrible read latencies for whoever that reader was. The async writes weren't really as critical, other than we may have some, in the old way, we may have some waiters that are waiting for a new transaction group to open, but really, typically, async writes weren't a big factor that we had to worry about as far as speed. So what we ended up doing was actually splitting these types of IOs into their own individual queues. So we now have a sync read queue, a sync write queue, an async read queue, an async write queue, and a scrub and resilver queue. This gives us the ability to actually tune each of these individually. And we can set kind of guaranteed minimums for each one. So this is the priority order as you see them here. Each one has a number associated with them, and in this case, I'm making these numbers up. They're actually different in the code, but this is just for illustration purposes. So in this case, we're saying sync reads have a minimum number of reads that they can issue, which is 5, a maximum number of reads, which is 10. Sync writes also have 5 and a maximum of 10. Async reads, you get a minimum of 1 with a max of 3. Async writes 1 and 10, and scrub is 1 and 2. So the idea behind this is as I/O starts to come in, you're guaranteed a minimum that you can actually issue at any given instance. And once you've hit your minimum, then you have to wait for somebody else's minimum to be met. So let's just kind of run through an illustration. So assume that this type of workload came in, where we had 2 sync reads, 3 sync writes, 3 async reads, and 5 async writes came in. The first thing we would do is start processing the queues. We know that sync reads have the higher priority, so we want those to go first. So we start to issue those. Now that we've issued them, what do you expect to happen next? We're expecting sync writes to go next. They're the next ones that have the higher priority. So we let those go. And eventually we're going to process async reads as well. So that's all great, but now all of a sudden we get more sync reads that came through. So what we have already in the active I/O queue is we have 2 sync reads, 3 sync writes, and 1 async read, and now this is what our queue looks like. Any ideas of what we would want to happen here? What we're going to do is we're actually going to look at the sync reads. They're the more important I/O types, and we're going to issue those. But we're going to get to a certain point where we're now going to stop. So what we've gotten to here is we've issued 3 more sync reads, but as a result, we've hit our maximum, our guaranteed min, which is 5. We have 5 in the queue at this point in time, and we're going to look and say, has anybody else not reached their minimum. And in this case, the async writes have not reached their minimum. So they're going to be the next thing that actually gets issued. And then after the async read gets issued, we then go back and issue the sync read, clear that queue, and in this case, we also see a scrub resilver IO come in right at the end. Question? So the question is, how did it determine to continue the sync read instead of, sorry, the async read?
Yeah, so it stopped at 1.
So let's,
Yeah, it only did 1, and then 5 showed up for the sync read. So how did it just not continue with that async read before doing the sync read as a priority?
so how does it not continue processing the async read? So what actually happens in this instance is we go back and look at all the queues, and we're going to look at them in priority order. So the question that we're always asking when we're looking at the queues is, we start at the top, which is sync read, it has the highest priority, and we ask, has it met its minimum guaranteed number of IOs? If there are IOs in that queue, process them. So we just issued the async read, we come back through, we're figuring out who to issue next, we start at the top, we go to sync reads, and we say, okay, he's guaranteed 5 IOs. How many are currently active? There's only 2. So let him process the next 3. So you end up with him processing 3 off his queues. We come back and ask the question again. Okay? Now that we've gone through, we start at the top of the queue and we say, sync reads, how many are you, we still have 1 in the queue. Why aren't you going forward? Well, he's got 5 in the queue already, which is his guaranteed minimum. But async writes, which is guaranteed 1, doesn't have anything in the queue, so he's the one that gets chosen next. So we process this queue and this algorithm every single time we determine that we want to issue something. Does that make sense?
Yeah.
Yes?
Can you set these floors and ceilings per data set in the command line?
So the question is, can you actually set these floors and ceilings per data set on the command line? The answer is no. They are tunables within ZFS. They're global wide for all pools. It's an interesting point, though. The main reason that you can't do this on a per data set basis is that at this layer, you're actually deep in the I/O pipeline, so you're kind of aggregating everybody's I/Os kind of coming through. So you would have to look at, there have to be more logic to actually say, okay, this particular data set is only allowed to have 3 and provide some kind of QoS, but that's definitely possible. So just out of curiosity, with this queue and this setup, what do you think gets issued next? So in this case, the next, if we were to look at this even further, the next thing we would actually issue is this scrub resilver IO, because he doesn't actually have anything in the active queue and he's guaranteed 1. Everybody else has already met their minimum. So another area that we've done a lot of work in is handling imbalanced LUNS. So the problem here is, it's great, you started off with this wonderful pool, you added some disks, you started filling them up, everything was great, and then you ran out of space. What do? You're like, oh man, I need to add some more disks, and you add them, and you're like, wow, the performance sucks. Anybody run into this situation? Gosh, you leave it to like awesome administrators, like be on top of it and never get to the point where their pool is full and have to add more disks. That's great. This actually is something that we're seeing in the community quite a bit. And it also depends on kind of the workload, especially if you have customers that are doing a lot of archiving and maybe didn't do enough capacity planning at the beginning and started off with some smaller disks. They've tried to expand them, but after a point of time, they really have to add more disks. What we've added in here is actually we're kind of taking this in multiple stages in OpenZFS, and the very first thing that we've added is an ability to actually force this new kind of allocation avoidance mechanism. It maybe is the best term for it. But it's this thing we call ZFS MG no alloc threshold, which defines a percentage of free space that makes a disk eligible for allocations. So the idea here is, as you start to fill up the disks, you get to a certain point, as long as that disk has free space, you can allocate to it. Once he no longer has free space, you stop allocating to him. So let's look at this, at how this actually comes about. So if we look at what the old algorithm used to do, you simply had disks, you're writing data to them, you're filling them up, you get to a certain point where you're like, okay, I am about to run out of space, I better go and add more disks. So I add new disks, and now I start striping across all of them because ZFS gives you that automatically. The problem is that we're writing the exact same amount of data across all disks. There is, in the allocation algorithms, there's actually a heuristic that tries to figure out to write more data to the devices that are imbalanced to try to bring them back into balance. But unfortunately, when you're in this situation, it's just not aggressive enough. You can't say, write gigabytes over here and give me, 512 bytes on these that are mostly full. So you end up in situations like this, where you keep filling the disks, but you're at like 99% and maybe 3% on the other devices. So how is the new enhancement different? Again, we have kind of a similar situation. We fill our disks, we add more, we start writing data, but this time we change how much data we write in a very aggressive fashion. In this case, that small block of data that's being written to the disks that are mostly full is typically 512 bytes. What you're seeing go into the other disks is in the order of like megabytes. So this scenario, you can kind of assume that what's happening here is you're cutting down your bandwidth of, instead of having 4 disks, you've really cut it down to 2. But you're cutting it down for a specific purpose. You really don't want to spend time trying to write to these 2 disks that are mostly full, because even though there's more write bandwidth, the time and CPU that you use is really taking all that away. Question, yes?
Do you specifically try to do metadata in the small writes?
So the question is, do we specifically do metadata on the small writes? It turns out that metadata is typically what gets written there, because all bulk data really is, unless you're doing 512 bytes as your record, typically will not compress to that size and will get written to the other devices. And then this changes. If you recall, I said that we have this new ability to define a threshold, a free percentage threshold. So once all disks hit that threshold, now everybody's eligible to start getting allocations. But what we've done is we've taken those 2 disks that were mostly empty, we've driven them up to be 90% full. I'm back in the same situation. If I'm in a bad situation, well, why not have everybody, be equally unhappy in the party? So we let everybody start taking the same bulk data. If you were to add more disks here, what you would see is, again, these 4 disks would probably start taking the small bits of data. Any new additional disks that you added would now take the bulk data. So with that in mind, now let's talk a little bit about some features that aren't available in OpenZFS yet, but are very, very close. I mentioned the imbalanced LUNS and how we're kind of doing this in phases. The next phase is the pool fragmentation. So we're introducing this new ability for you to see how fragmented are your devices and create a calculation for your pool. So you'll see here this new fragmentation metric that shows you how fragmented your pool is. Now what's interesting about this is, as we start thinking about this problem, we can then make some smarter decisions. In the previous slides, I mentioned how you hard code kind of this free threshold. Well, what if we use the fragmentation metric as a way of deciding where and which devices we actually do allocations to? So you can see kind of the progression, that, or at least our mindset of how we're going to move forward with this and dealing with this particular problem. The other interesting thing that we're adding is this thing we call zero block compression. What you have here on the left is a typical block pointer that is used by ZFS. This is the descriptor that shows where data actually lives. It's actually a 128 byte structure, and what we're doing is if your payload is small enough and compresses very nicely, it may not compress to nothing. So today, ZFS, if you have compression enabled and it compresses away to nothing, then we simply don't write one of these structures. But what if you had just enough data where you needed to actually go write that single sector block? Well, that means that every single time I try to read it, I have to go through this. I have to read my indirects, and then I get to my level 0, and I have to go issue another read to pull that single sector read off disk, so I've just issued another I/O. But if I could embed that data into the indirect block pointer, now I have the ability of saying, if it's small enough, I can avoid the reads altogether. I simply get my metadata, and inside my metadata is this piece of data that I can use. The key behind it is it has to be 112 bytes or less. So we've taken the block pointer and we've effectively stripped out most of the pieces that are used to describe where data lives and embedded the payload inside of it. And there's many more things to come. So there's lots of things already queued up from all sorts of different companies and all sorts of different platforms. But I think now is probably a good time for me to start taking questions. I'll throw this slide up, and just in case you want to get involved, there are many ways. Definitely contact us on OpenZFS.org. The cool thing is, if you have a company that's involved in OpenZFS, and your logo isn't on the back of the shirt and you want it to be, definitely get in touch with us. If your administrators using OpenZFS, spread the word. Let people know. But that's pretty much all I have. Questions? Yes?
Going back to this fragmentation slide you had, and adding additional ones, you stated that you were just basically going to make the default and writes and the 2 new ones. Is there a feature where you could, somewhat like a scrub, but in this situation, basically distribute the data from these two full ones to the empty ones, so you remove this fragmentation?
So the question is there a feature coming that would allow us to remove this imbalanced fragmented LUN and redistribute the data across any new LUNs, correct?
Yes.
So it's interesting. Many of you have probably heard about there was a block pointer rewrite project that was being driven out of Oracle for some time. And we're intimately involved with it. But we decided that we don't want to implement that in OpenZFS, primarily because it was a grandiose project, had a lot of wonderful benefits that would have come with it, but it was also kind of a stopping point for development, in the sense that it touched so many different layers that it was going to make it very difficult to add additional features afterwards. That said, we've decided to take a very different approach to dealing with these types of problems that BP rewrite was going to handle. One of them is, how do we deal with something like this? And we have a very good idea of dealing with this problem by introducing kind of a device removal logic where you could effectively remove this and recreate a new virtual device that looks like this, but then gets data redistributed to it. So we already have a write-up on how we want to do device removal going forward. We're still tweaking it, but there are solutions that will potentially deal with redistribution as well as device removal and handle this problem all in one.
Can you address how the new combined development process is going to feed back into the various things that we actually use?
So, so the idea behind the development process is we're going to, one of the big things that we want to address initially is taking all the platform-specific layers and teasing them apart. So creating these platform-specific porting layers for each of the various platforms and coming up with a common ZFS repository that allows any of the platforms to actually simply take that wholesale. We're coming up with a testing facility which is available today in the open source community that will then make it easy for you to test. So whether you're doing a development on Illumos or development on Linux, you test with the same test structure, and we can be guaranteed that it's going to be the same on all platforms. There's a lot more on the development cycle that I can go to. So if you have more questions, see me at 2. By the way, I have a 2 o'clock guru session. I'm happy to take more questions there because I'm sure we're really close on time. But yes, question.
Do you have any advice for those who still have pools on good old Solaris but may want to move to this world in the future?
Great question. You know, I think if for those that are doing migrations, it's probably difficult. In many cases, the easiest thing to do is probably going to be do like a ZFS send from one pool to the other. Although I believe that Oracle may have even revved the file system version recently, which might prevent you from doing that. I'm not 100% certain of that, but I think that in one of the new releases they were adding some feature into the send stream or the data set which bumped the version, so making it kind of incompatible. That's a little unfortunate. We don't have insight into like how to reverse engineer some of those things. I'm sure that, I mean, there are community members that have been looking at like some features that are in Oracle and trying to figure out how do you make those compatible. But at least today, the best thing I could tell you is if you're running, I think if you're running Solaris 10, you probably have a very good shot. If you're running Solaris 11, your chances are a little lower.
Is there a particular Oracle/Sun version number to avoid exceeding, for example?
So I think as long as, if you're running a version of the pool that doesn't have encryption or RAID 0 mirroring, so version 28 or less, you can simply import the pool.
Okay.
If you are running, I think the last version of the data set is version 4. I can't remember. It's either version 4 or 5. I'll double check and get your name, but if you stay...
No, I mean, put it on the website.
Definitely.
Yeah.
That's actually a great idea. We'll add some comments on like how you can try to be compatible and a way to do migration. That would be awesome.
Thanks.
Yes, question.
Is Oracle interested in any development effort that you guys are doing, or are they just kind of going off and doing their own thing?
Is Oracle interested in any of the development efforts that we're doing, or are they going off and doing their own thing? To be honest, I don't really know. They're definitely doing their own thing. And we're happy to make like the feature flags, and actually have talked to some, I have colleagues and friends that still work at Oracle. So we've talked to them about feature flags and and effectively what they would have to do to implement that. It would be awesome to get to a point where Oracle decided to do a feature flags port, so that way at least pools would be compatible, whether you're running Solaris or you're running Illumos or FreeBSD. You could come in and use the same feature flag mechanism so that you could make pools that are read compatible or pools that would actually import if the feature hasn't been enabled. But they have their own agenda and they have their own business needs. So I don't know exactly how much they're looking at the community. I will say, for example, like, the community is definitely interested in some of the things that are going on in Oracle. One of the things that is on here that Oracle has already implemented is larger block support. So that's something that we've been interested in for a while. Oracle already has it, so we think good ideas can come from anywhere. And as a community, it's just a matter of getting people behind it.
You have to call questions there. Thank you, George.
Yes, and I have a 2 o'clock session. I'll be giving away lots of T-shirts for people, and if you ask questions, please see me afterwards. You get a free T-shirt with that, but come to the 2 o'clock and you get another chance for it.